Yes, I'm going to talk about this work. I was told that people here, I feel like this is probably a diverse collection of backgrounds. So I have more content than I'll probably be able to get through, but feel free to interrupt if anything is confusing. And,
yes, we have a second seminar on Wednesday at 11 a.m. For those of you who can't get enough of this talk.
Yeah. Just feel free to interrupt with questions if anything is confusing, and I'll try to go slowly. So our starting point is in complexity theory. So it's this class that we call NP, or non-deterministic polynomial time. It's basically like you should think of it like the kinds of computation that you could efficiently check with a classical computer. Really, the thing I wanted to I guess the right starting point would have been MA, which is a slightly related class, but in NP, basically there's a prover that sends you a classical proof, and you can check it, in efficiently or in polynomial time. And at least the way that I think of these is kind of like statements about math, like it's something someone could write down a proof of. Now we think that we should be able to build quantum computers. So I think in the early 2000s, people were thinking about how to generalize this class to account for the fact that Arthur could be a quantum computer. And there's actually two different ways you might imagine talking about the quantum version of this kind of provable statements. So the first one is actually, if you want to make the fewest changes possible, the first thing you would come up with is to just have Arthur, the verifier, be a quantum thing. So this is what we call QCMA. And I think the naming is probably messed up. It's a historical thing. It's supposed to be quantum classical, and then it maps onto Merlin Arthur. Merlin is the wizard, and Arthur is this verifier, the knight doing something. So QCMA is very similar to NP. There's a classical proof and a quantum, but the only difference is that Arthur is now a quantum. I hope that all makes sense. And if we get rid of the C, we end up with this class called QMA. So, the only thing we've done now is just made the proof quantum. So, I don't know, morally, I think of QCMA as things I could, okay, so when we say that Arthur is quantum, really it's kind of we're trying to verify some property of the physical world. There's a superconducting material at room temperature. And QCMA is kind of someone wrote down the formula for you so you could make it yourself. And QMA is kind of someone gave you a sample of it. So you test it, but you don't actually know what it's made of. So that's how you should think of these two classes, at least if you're a physicist. And it was kind of proposed as a question, I think in 2003 by some survey paper, hey, there's these two versions of quantum, provable statements when you have quantum computers, and are they equal? You might care, you might not, but at least I think it's a really cool question because we think of QMA as kind of QMA encodes a lot of problems you want to solve, not just in computer science but also in in physics. So it's a quantum analog of constraint satisfaction problems, and it turns out to capture a lot of the kinds of problems you want to understand from physics, the ground energies of local Hamiltonians, representability of fermionic systems, and other things. It turns out you can map a lot of problems from physics onto this class into QMA. And if QMA was equal to QCMA, so if these two things were equal, it would be kind of an interesting state of affairs, because anything you could prove by getting a ground state, you could also just write down something on a piece of paper that would verify the same property. It's kind of we wouldn't need to send quantum states ever. You could always just turn it into something classical. And on the other hand, it's the other alternative is equally strange, which is that there are some ground states of local Hamiltonians that you could never write down. You could, if you're trying to verify a particular property, there's literally no string you could ever write down that would prove this property, but there's this quantum state that you could use to learn something. So it feels both of these are interesting, states of the world. So yeah, in a single sentence, I guess studying QCMA versus QMA is kind of are the relevant or interesting properties of these quantum ground states possible to write down classically? So this is like the meta question we're trying to answer. Does that make sense to everyone? Yay. Okay. So what can you say about it? Well, you could try to prove that they're equal, but I don't think that. So I don't want to prove that they're equal. You could try to prove they're not equal, but that would run into like some really big open questions in computer science. So it feels like you would have to first, for example, prove that P is not equal to P space before you even started to like think about proving that this like kind of statement outright. So the next best thing is what we as computer scientists call an oracle separation. This is kind of like evidence that they're separate, but I'll explain what this means. So an oracle separation is kind of like, imagine that you like hide some kind of functionality in some, what we call an oracle. You can think of it like a black box or like a little machine that someone gives to everyone, and you can like access it, but you don't really know how it works. So the standard sort of oracle separation is this like second thing I've written, which is what I call a classical oracle separation. So it's basically like, imagine that Arthur and Merlin and everyone in the world had access to this magical function, which I'll denote as O, and they can like query it, so they can like give inputs and receive outputs, even in the quantum superposition. But no one like knows the actual like code of it. I guess like if you could query every point, you could like write down a truth table. But anyways, and then in like around 2000, this notion of like a quantum oracle separation appeared. I think motivated by this problem of studying like QMA versus QCMA. In that world, like everyone gets access to these like quantum unitaries. So like everyone can like just press a button and some unitary gets applied, and then they want to learn some property with that unitary, say. So yeah, I'll go through this a little bit more like in like 5 minutes, but basically for this kind of problem, or like problems where like everyone is quantum, it's kind of like, yeah, it's like a lot more challenging to prove a classical oracle separation than a quantum oracle separation for this problem. And I think the next slides will go through some of the history. So our result is to prove a classical oracle separation. Yay. So I'm going to go through some of the history. I'm not going to explain too much in detail like what all these things mean, but yeah, hopefully for those of you familiar with the problem, this should be pretty familiar. This was first proposed in 2002. I think in this original paper, actually, it's kind of funny. They like Harnav and now they like wrote this like blurb about QMA and QCMA, and they're like, oh, they're probably just equal because like you can just look at the marginals of your quantum state and write them down. It turns out determining if a quantum state matches a bunch of marginals is as hard as verifying ground energy. So you know, kind of that idea didn't work out. And then 2006. Aronson and Cooper gave the first like quantum oracle separation. This is like, it was basically evidence that they wouldn't be equal, and the oracle is basically like a flip around a Haar random state. So when I say flip, I literally mean like as a matrix, like it applies a -1 to like a rank 1 subspace, and that thing is random. And then since then, there's been a bunch of these like either candidate proposals or like not quite classical proposals. So sort of in the early, like 2011, there was like the proposal, but Ludomirski didn't give a proof. He just kind of like said, hey, maybe this problem separates them. Befferman and Kimmel gave the first of these like non-standard oracle, classical oracle separations. So in their oracle, they imagined everyone got a box, and instead of like describing a classical function, it like applied a permutation for you. And then, yeah. In 2022, Anand Natarajan and Chindarike, they were able to prove like this distributional testing oracle. That means like it's like an oracle that's randomized, but you only know about, like it becomes re-randomized after you query it. It was also like one of these non-standard classical-ish oracles. And then recently, like in 2025, there were like a bunch of papers that proved a pair of papers that proved like conditional oracle separation, meaning that like they made some conjecture, and then like under that conjecture, you can separate QMA and QCMA. I'll explain, but the one that I omitted from here is actually the oracle separation that like leads to our work, although we don't like. So in that paper by Mark Zandri, he like made a particular conjecture that turned out to not be quite true, and but we take his oracle and get a separation nonetheless. Before I explain any math, or before I do anything or explain anything about what we've done, I'll just give to me why has this problem been so hard? 'Cause like I said, it was proposed in 2002. It's been 24 years since then. So you might wonder why was it so hard to do this? And this is maybe going to resonate more with the computer scientists, but I feel like a lot of things in computer science, there's kind of this tension between structure and randomness. So in if you wanted to separate QMA from QCMA, you might think okay, well, what are the things that we know that quantum computers are good at? Well, they're good at finding some kind of hidden structure, right? A quantum state could maybe point you to some correlation that you wouldn't have been able to find if you didn't have that quantum state. But if you wanted to encode this into a classical oracle, it means you want to make the oracle kind of structured. You want to pick it very carefully so that it has this correlation that a quantum proof tells you about, right? If it's a random oracle, what's a quantum proof going to do for you? So in some sense you want to have a structured oracle, and indeed all the proposals are kind of highly structured, so the expander mixing thing proposed by Ludomirski is kind of on a graph, and you pick it to be an expanding graph. The Yamakai-Zandri one has some hidden, has a code, it has an error correcting code associated with it, so it's very structured in that sense. And sort of in these proposals have gotten less and less structured. So actually the one I'll explain is what I think of as the least structured of these oracles. It just has sort of the minimal possible structure to have a quantum state help you. And on the flip side, it's really hard to analyze structured oracles. At least the techniques that we have, they work really well for really random things. If you have a truly random oracle, then we have all these nice techniques for proving bounds against them. I've written the polynomial method and the compressed oracle method here, but there's a bunch of adversary method, but they tend to work best when the oracles, when the thing you're querying has less structure. It kind of makes sense. If there's a lot of structure, you worry that your quantum algorithm will actually do very well. So the things that we know how to bound are these super random, almost maximally random objects. And this is, not so good because we're trying to build an oracle that has structure. We can't really prove lower bounds against it, so we can't say it's not in QCMA anymore. So basically the high level of what happened is that in 2024, Mark Zandri proposed a very, a sort of less structured version of oracle separation, and we're able to introduce some new analysis that allowed us to analyze the kinds of oracles that he wanted, which kind of bridged this gap. So that's sort of the very high level of what happened and why I think it's taken so long for us to prove this kind of classical oracle separation. So hopefully that makes sense. Okay.
John, how significant it is to if we had of evidence it is if we had oracle equality, and what kind of oracle would give us there exists an oracle such that QMA is equal to QCMA. Would such a result for some oracles be interesting and provide as strong of an evidence for inequality as your results?
Yeah, I think that with oracle separations, it really depends on the oracle. I could just say that QMA and QCMA are equal relative to an RE oracle or something extremely powerful. But I guess here's where the art of computer science comes in. Really how much evidence you think it is depends on how realistic you think the oracle is. So yeah, if you found a very natural oracle or object under which, or a thing under which they're equal, that would be a lot of evidence that they are. I'll explain to you I'll get to what our oracle is, but I think it's actually probably the most natural oracle. It actually is literally just you just take one of these, a problem that's QMA complete, and you just imagine you do the same, so with SAT, we have these SAT instances, but you could imagine you just got a random function. In a similar way, you can take like a natural family of local Hamiltonians, and just imagine like you didn't see the structure, you didn't see the local terms, you just got oracle access to it, and this is the separating oracle. So I feel like it's sort of like a very natural idea. It's kind of like saying like, in the same way that you could never hope to prove that like P is equal to NP unless you like use something interesting about a SAT formula. It's like you can never prove that QMA is equal to QCMA unless you really use something interesting about like pairs of SAT formulas, like in the standard atom cases. So, anyway, I think, yeah. Like, to answer your question,
has there been historically some results on the equality side? Showing
I don't know about any.
Okay.
Yeah, I feel like most people. I feel like almost all the work has been on the non-equality side. Like, so for example, like there's been a long line of work for like proving quantum PCPs, and in some sense, if you proved a quantum PCP, it'd be kind of like giving evidence that it should be hard to like classicalize quantum states, or like there shouldn't be like load-up circuits, like this NLTS conjecture that people think. It's like there's no like way to take the ground states and write all of them in like a small circuit. So I think people have been working in this direction, but who knows?
If quantum PCP is true, then it's a strong evidence that they are not the same.
Yeah, I think that's true. Maybe Thomas knows better.
Yeah, to me, it feels like it should be an evidence that they are equal, because there is a short proof. There's a very short quantum proof, so you have a better chance of like turning that into a classical. Don't you think so? Like if I can, like the proof version of quantum PCP would be like if I could look at a few positions, then I can verify something, right? So that few positions might be, we might have an easier time to turn it into classical. Anyhow, like you could just look it up.
I said QMA equals NP, right? So.
It would. Yeah, it would. So, that's right. Maybe. Yeah. All right. Thanks.
Yeah. Sorry, I'm gonna take my time. I'm a little jet lagged, so I'm tired.
So is there anything known about random work over there? Like, is it equal for random work or nothing?
So I know people prove these like there's like a quantum like QC hierarchy, like polynomial hierarchy thing, and I know that's like infinite under random oracle. I don't actually know if I don't think it's known if QCMA is not equal to QMA under random oracle, but I also don't know if they're equal. Yeah, sorry.
Why is your bosonic compressed oracle more structured than compressed oracle?
I mean, okay, like behind, like, they stem from like the same idea. So it's like, really you could, if you wanted to be a critic, you could say we didn't do anything new. We just like looked at like, what happens when you purify, a system, and just happened to write down a different concise form for it. So it's like kind of the same thing, but it's just, yeah, it's just a nicer way to analyze things. I guess not everything's the same if you want to think of like, we're all just like, writing things as in different forms and like, but yeah, the idea is kind of the same. You start with some random family of oracles, you like, and I'll explain it, but yeah, it's not that different, but it just gives a different perspective on compressed oracles.
You are trying to get to, from this result of geometry that is not very structured, you want to get to a structured one, which is your result.
No, I want to take this like slightly less structured oracle
And have no structure.
And be able to analyze it. No, I want to keep the structure. The structure will be important for like proving containment in QMA, but I want to be able to prove lower bounds against it, right? So I want to be able to prove that like even when querying this like structured oracle, like a quantum algorithm with classical witness can't tell me something about this oracle. Does that make sense?
Is it possible to kind of elaborate a little bit on what makes a oracle a structure? But I mean, I know that you gave some explanation. I didn't catch it.
Yeah, I mean, in this case, I mean, I think it's maybe like, no, it's not going to be nice. Okay. So like in our case, like what I mean by structure is like you have a pair of functions and they're like, for example, they're like, so like, do you know the correlation problem?
Sure.
It's like you have two functions and they're related by a Fourier transform. So like this is what I would describe as like having some kind of global structure. Like they're like kind of like highly structured. Like you wouldn't get like every function or every pair of functions from this. Like uniform probability, you're kind of, there is like some structure encoded in this thing. And the problem that we'll consider is kind of like a generalization of correlation. So that's the kind of structure. Yeah, okay, cool. So before I get into the meat of things, I'm going to explain what these like Oracle input problems are. It's kind of like how I've been thinking about Oracle separation. So like, you know, like I said like an Oracle separation is like everyone gets access to some like function in the sky. But another way to think of it is like you're really just proving bounds against like polylog time verifiers. So like instead of like having the Oracle be like a big function you can query, imagine like you are like a little tiny guy and you get a normal sized input. You can access the input like quantumly. So you can describe like this whole family of like Oracle input problems in this like scaled down world. So there's some language, you know, of yes and no strings. So like you're going to be given a string and you're asked to decide if it's in the yes bin or the no bin. Our input, you know, I'm hiding things, but like n you should think of it as like 2 to the n, to the little n. And our verifier will get a little tiny, so remember like n, little n is like log of big N, so polylog of big N sized quantum state, and they get to make controlled quantum queries to this Oracle, this input. And they have to do this decision problem. So basically like you're going to be given a string, and you're promised it's either in the yes or no bin, and you have to decide you know, with the 2/3, 1/3 gap. So like if it's in the yes bin, you have to output yes, there's probably 2/3. If it's in no bin, at most 1/3. Okay. And we can do the same thing for QCMA. The only difference is you know, instead of receiving a poly little n bit quantum state, you get a poly little n bit classical string. And it turns out that so this setup is like slightly different than the Oracle separation I described earlier, but there's kind of a standard trick for turning these kind of like scaled down problems into like standard Oracle separations. So for the rest of the talk, I want us to think about these like proving bounds against little tiny QMA algorithms. So yeah, hopefully that all makes sense. So now I'm gonna like tell you what the problem is, and you know, thanks to Hamoon's question, I kind of already like set it up. So if you guys are familiar, so maybe I should have like put more slides here because I didn't know what people would be familiar with, but there's like this very famous problem in quantum computing called the correlation problem. It's kind of like this, you know, like used as like a separate, like to show that like quantum computers can like detect global structure that classical computers shouldn't be able to detect. And it basically, I'll just explain what's going on here. So our problem is like generalization of that problem. So imagine you got pairs of sets, S and U, and I like to, you know, talk about them as if they're like actually on some like physical floor or a wall. But so you know, you know about these two sets, S and U, and you imagine that S is on the floor and U is on the wall. And by this, I mean like the standard basis is on the floor, and the Hadamard basis, which is another way of viewing the same objects, is on the wall. And you can imagine there's like some quantum state in the middle, right? And we say that two sets, S and U, are like alpha specially correlated if there's some state that like whose shadow on the floor and shadow on the wall is like pretty high. So here you see like if you want to like think about it this way, like you're taking psi and you're like projecting it onto pi s. So it's like you're forcing it to be correct with the floor, and then you're doing the Hadamard transform and looking at it on the wall. And you're asking like, is this shadow on the wall like have like high overlap with the set U? Okay. And the particular question we're going to be interested in is sort of the natural one that would come up is like I show you a picture on the floor and on the wall, and I ask you like, is it consistent with some quantum state? Okay. Yeah. So this. Yeah. Feel free to ask questions because this is like. Yeah.
What would a state like look like if it had a large overlap in the two bases in the definition that you gave? If alpha is like really large, maybe what is it like? The largest it can be is 1. What does that mean? What would that mean? Just trying to get a sense of like what these states look like.
Yeah, so I guess it depends on what the picture on the wall and the floor is. So like, if for example S and U are like everything, then like any state would work, right? Like every state is supported everywhere on both bases. So, but as I like start to cut out like parts of the floor or the wall, so I like make smaller sets S and U. It's kind of hard to characterize like what.
Oh, what are S and U again? So.
Oh, sorry. S and U are like two sets of like n bit strings. So subsets of n bit strings.
Little n and bit strings.
Little n bit strings. Sorry. Yeah. So like think of it as like I have like 2 to the n possible like positions and 2 to the n like momentums or whatever, like Hadamard bases things. And I'm gonna ask you like, is there some quantum state that's like supported in like on these positions and in the Hadamard basis mostly supported on these momentums?
Should I think like, so S would be like a subset of like computational basis strings, and then U similarly, but for the Hadamard basis.
Yeah, you should, like, they're both actually the same, like they're both just subsets of computational basis strings, but we're going to interpret U as if it was like in the Hadamard basis. Because the question will ask about that. Yeah.
When you're in the no case, you mean for every state, right? Or
Yeah, exactly, yeah.
it's existent for every. And the
Yes.
57 and 59, like
The 57, 59 is not,
they're a bit unusual.
yeah, it's just, so like, it'll turn out there's some points in the proof where like, it'll be good to have a constant that's less than 1, and we picked 1/10. So then it kind of became like a 2/10. Or, sorry, we picked like 1/10 in one spot and then like 1/10 somewhere else, and it kind of became a 2/100 gap. But as long as it's constant, it's...
But you're going to give us later a distribution on pairs of sets?
Yeah, exactly. Yeah. Yeah, so like Thomas said, sorry, the problem is really asking about the spectral norm, which is why it's called spectral correlation, of pi u h tensor n, pi s. So it's, but I've written it as a side thing to make it obvious where the state should come in. But,
How is this related to the original correlation problem?
yeah, the original correlation problem is like very similar, except you know that the state is going to be like all zeros, or I think plus tensor n, sorry. So like, it's like I have two functions. In this case, like the functions are going to be quite. So okay, in our case, you should think of S as like a very sparse set, but in the original correlation, you should think of like the S as being like a random set, and then the wall or the U as being like its Fourier transform. And then like it's like if I started with the state plus tensor n, it would have pretty high overlap on the floor, and its Hadamard transform should also have like pretty high overlap on the Fourier transform of what's on the floor. So, yeah.
Naturally, when S is a small, U is going to be large, right? It's kind of, there is this like uncertainty sort of thing.
Yeah. So I mean, this is like a bit of history, and I'm happy to talk about it. But in Mark's original paper, he like conjectured that U would be like something that looks uniformly random. So S would be sparse, and U would be just like a random-ish set. Yeah.
Okay.
What's your name?
John. Yeah, not John. I guess we talked about this on Wednesday, but I'm just wondering, the sets S and U, do they have to be countable and discrete, or and when you come up with a structure, do you like start with this premise, or do you like work backwards from a continuous string?
I am a computer scientist, so
okay. Sorry.
I don't know much about how to analyze continuous. That sounds like a very interesting question, but yeah, actually you'll see that, like for example, we have this H tensor n thing in there. Like Mark's original paper had the QFT like over capital N, but we were like, this is like
Too much.
yeah, I can't work with this. So we did a lot of things to simplify it to make it more computer sciencey. But yeah, we could. I think you could also. I don't know what the interpretation of this as like a.
I mean,
continuous system.
you're already making all of these physics analogies with position and momenta, and in physics there's this thing that's called the Wigner function, which is the Wigner function, which is like a picture of a state, and you have a position on the momentum basis in the projection. I think it's not related, but I think there are more physicists use it.
You know, when I was working on this, and also after this paper came out, I've been going around ever asking a bunch of people who do physics, like if they've seen these things, and I feel like it's never like, maybe I'm just querying them wrong, but I feel like I never get them to give a good answer, but I always get random people who like I give this talk to, and then like they're just like, oh, that's just this, and like that's good to know, but yeah, good.
I found another separation.
Okay, so the first thing, just to get this out of the way, let's just like quickly see that spectral correlation is in QMA. So the proof will be that the prover gives you a copy of this state psi that maximizes the spectral norm, and you'll just use your S oracle. I like to think of it as like shining the light. So like you'll actually like look at its shadow, but in the actual quantum verifier, you'll use the S oracle to make a measurement of this POVM, which is like projection onto S and projection on and its orthogonal projector. And if you get the outcome no, like identity minus pi s, you just reject. And if you see the outcome that it is supported on pi s, then you're like good to go. You apply the Hadamard to your state, which is I think of like rotating the light, and then you do the same thing. So you measure pi u. If you see outcome identity minus pi u, you should reject. Otherwise, accept. The probability that this algorithm accepts is literally just this norm squared of pi s, h tensor n, pi u. Okay. So by the definition of the problem, like this thing will be bigger than 59 over 100 in the yes case and smaller than 57 over 100. Like there will exist a state which is bigger than 59 over 100 in the yes case, and for all states it'll be smaller than 57 over 100 in the no case. And you can do some amplification, the standard techniques in quantum complexity theory to bring this to standard 1/3, 2/3. Yeah. So the rest of the talk and the sort of the hard part is proving that this problem of determining if there's like the state that determining the spectral norm of this pi s, h tensor n, pi u is not in QCMA is going to be sort of the main focus of the rest of the talk, and where we like have a lot of the new ideas. So this appeared in like Mark's original paper from 2024. So. Okay,
could you just very quickly remind us what was the problem that was in QMA? You are given an oracle S and U,
yeah.
And you want to determine whether there is a state that has the governor.
Yeah,
right.
exactly. Okay. So, like Thomas said, we're gonna define a distribution over spectral correlation instances, and we're gonna think of this as like the hardest, like a hard distribution to prove with a classical witness. So, I'm gonna go slowly and let me know if anything is confusing. Like I said, I'm gonna take the set S to be a really sparse set. So, what I'm gonna do is imagine sampling 2 to the n over 10. Like random elements, these are random bit strings, S1 through SL. Right, so I just like splatter them on the ground, and now I've got like this sparse set. Okay? Now, the state that I'm going to want to encode, so remember there's like a state, I'm going to pick the witness, basically I'm going to like pre-choose the witness. It's going to be this subset state, uniform superposition over these points. I think this version of the talk doesn't have the thing, but yeah, just like it's going to be like 1 over square root of L times sum over I, like ket SI. Okay, sorry I didn't write it in the slides. So that's a state, a quantum state, and okay, it's not quite normalized because the SIs can have overlap, but let's ignore that for now. And I want to take U, the points on the wall, to be the heavy points of H tensor n. Right, so I'm going to take the Hadamard transform and I'm going to sample for every bit string, I'm going to include the bit string with probability that's like proportional to this number here. Can you see my mouse? No? Okay. You should think of it as literally just like when bra y, H tensor n, ket s is large, this number is large, and when it's small, this number is smaller. So yeah, basically like this probability distribution is something that's meant to like correspond to like the heavy points of this state, ket s. Does that make sense? And I'll just sample those points to get a random, distribution over S and U pairs. Okay, and I'll call this thing strong, and I'll also call this number here, we call it gamma y, just for conciseness. So, does this distribution make sense? Basically, I'm like picking a distribution for which there will definitely be or like with very high probability, be a good witness, this like subset state. And the goal is going to be to show that like no classical witness will be able to prove to you that this subset state exists. So I'm going to call this distribution strong, and for reasons that will become clear in a few minutes. But yeah.
So can I just ask, so here the good witness, let's say we allow the two states to be different, so one of them will be get S, but the other is not quite get U, like you need phasors to get the absolute values right. At first I thought the way you're presenting it, the witness is get S, get U, and I was surprised that there's no phasors.
Oh, what do you mean by ket U?
Like the same as get S, but for U.
But the ket U is gonna, like in theory, be equal to like Hadamard transform applied to ket S.
No, I mean here you define the set U.
Yeah.
I define ket U from that set.
Oh, I see. Yeah, no, we're not going to talk about a ket U. Yeah.
Yeah, so there will be, okay.
Yeah, so these are going to be a family of yes instances, and I'll explain in a moment like what the no instances are going to be. But yeah. Before that, let me just give you like this is going to be a pair of theorems that will like basically taken together prove the separation, but it'll give you a sense for how the rest of the talk is going to go through. And if I can get through the first of those two theorems in this talk, I'll be very happy. So that's the goal. Okay, so the first theorem is like, given a sample, if you came up to me and claimed that there is a QCMA algorithm for the spectral correlation problem, then there's actually an algorithm that takes as input just the U oracle, so like, it doesn't even look at the S oracle, and is able to output many, many points from S. Right? So like, you should think of it like, when you're thinking about like, you know, our starting point is like to go by contradiction. So it's like, if you came to me with a QCMA algorithm for this problem, I should be able to do something like fantastical, like something, I should be able to solve some crazy hard problem. And what we should think of as like a crazy hard problem is finding a bunch of points from this sparse oracle. Like these points that are in the S set are like extremely tiny fraction of the total number of points. So like 2 to the n divided by 10. So like the probability that any random point is in the oracle is, you know, 1 over 2 to the 9n over 10, so extremely tiny. And so this is going to be how we get this like contradiction is, if you came to me with a QCMA algorithm, then I will somehow be able to find a lot of points from this S oracle without looking at it. I mean, even if I did get to look at it, it would be hard to find the points, but yeah. So, yeah, sorry, the first theorem is, I said it backwards, sorry.
Yeah.
The first theorem is that that this problem is hard. So the sampling problem, like finding points from S, is going to be a hard problem, even relative to U. So even when I give you access to U, it won't tell you much about the points in S. And the second theorem is this thing: if you came up to me with the QCMA algorithm, then I would be able to find these points in S with like higher probability. So does that make sense? Sorry.
Maybe elaborate a little bit on theorem 1. Theorem 2 you elaborated.
Yeah, theorem 1 is just saying like there's a nice picture we sometimes draw, but it's kind of like you like stand on the floor and you look at the wall, and I ask you to like point at things on the floor, right? Like if you were only looking at the set S by itself, then there's kind of the standard theorem from complexity theory. It's like the BBBB lower bound that says like you shouldn't be able to find a point in the sparse oracle with very high probability.
Even if you have S.
Even if you have S.
It's very difficult to find out the points of S.
Exactly.
But if you have U,
you might be concerned.
I see. I see.
Like it's not clear a priori, like, you know, because U is not sparse anymore. U is like the moral of the BBB's theorem is kind of like S is so sparse, it's like basically the identity for anyone who's like looking at it. But U is not sparse. U has lots of points. You can like see ones and zeros all over the place. So that, you know, this kind of idea definitely doesn't work to bound U. So like you need some new techniques there.
And where is your hardness? Like I don't see any. Like it's hard in what sense?
Like it's just like any quantum query algorithm that makes T queries to U and outputs V points from S will be correct with like this probability. And you see here that it's kind of like 1 over 2 to the n, like to the V. So it's like something that scales, like it's extremely small. Like doubly, if I take V to be like poly n, this is like doubly exponentially small. in N. Okay, so
What is strong?
oh yeah, strong is the distribution I had on the previous slides. This is a distribution over oracles, and this probability in the first theorem is like over this distribution.
Like the way you wrote it, it sounds like proving everything for v equals 1 would be just fine. So,
Oh no, so yeah, so this is kind of like the other moral. You see there's like a 2 to the minus q on the second theorem?
no. Ah, I missed that. Okay,
Yeah.
good. Okay.
So basically it's kind of like saying that the witness could encode for you like
yeah,
you know,
that's
q points of s. But if I take v to be like 2 times q, then it's kind of, I get a contradiction there. Yeah. Okay. Good. So this is just like a scaffolding. So we're gonna start going through them. I hope the slides are correct. I think they should start with theorem 2, but yeah, that's the one I want to get through. So I guess the first thing I'm going to do is explain why I call this strong. Because you might be like, well, what, you know, it's called strong, but I don't see why it's so strong. It just looks like a normal distribution to me. So we're going to call a pair S and U. Remember, S is the standard basis and U is the Hadamard basis. We call it strong, a strong yes instance, if not only is it a yes instance, so there is a state that is bigger than 59 over 100 overlap with both the floor and the wall, but also if I restrict the floor to be any small subset, then I must get a no instance. Okay, so this is a definition. Let me explain why. Like, the very first thing you would think of is like, well, like, okay, so the prover can't tell me all the points of S. But maybe they'll just tell me some polynomial mini points on the floor, because they can find them. The prover can find them, so maybe the classical proof will just be a bunch of points that are in S. And I want to argue, like the very first step you have to argue is that if you just know about polynomial in little n mini points on the floor, that must be a no instance. Because that was a yes instance. If that had a state which like had good overlap, then you could construct the subset state and like, or you can construct some state supported in those small number of points and then check the correlation or check the overlap. So sort of like being a strong yes instance is like the bare minimum. Like we've ruled out like the most naive like prover strategy, which is just to like tell you a few points on the floor. Okay?
What was L again? Could you?
L is the number of points in S. It's like 2 to the n over 10.
I see.
Yeah.
If you have anything like hundreds less, then you want it to be.
Exactly. Yeah. Like until the prover tells you basically almost all the points, or you know, constant fraction of the points in the S set, they can't like this simple strategy won't work. Of just like they tell you the points and they tell you a state you should like that's supported in those subset of points. Okay, and you know, maybe I'll skip over the proof of this claim in the interest of time, but you know, the reason why it's called strong is that we can prove that this guy is exactly a strong yes instance. Actually, the proof is kind of like elucidating, so maybe I'll just like talk about it for a second. Remember I told you that like the Aronson-Kuperberg oracle was like a reflection around a Haar random state, so it literally is encoding some like random state. Well, it turns out, like, if you write down the expectation over this distribution, like, you can just, like, compute the entries of this matrix, and you'll get that it's exactly, like, 1/2 identity, so this is, like, 50%, this is, like, and then plus, like, 1/10 of the projector onto this particular state, like, the subset state for S. So, this is kind of, like, why this oracle is, like, a classicalization of this Aronson-Kuperberg thing. It kind of is doing the same thing. It's, like, encoding a rank 1, like a one-dimensional thing you have to check. In this case, it's not like a Haar random state, it's like a subset state, but if you're familiar with quantum like cryptography, it's actually known that like subset states are like indistinguishable from Haar random, so it's kind of like, it is kind of like hiding a Haar random state in an oracle. Yeah. Does that make sense to everyone? The main thing I want to get you guys understand out of this
The
talk.
Anderson Cooper, I'm so sorry.
Yeah.
The Anderson Cooper reflection was what? Like identity minus 2 times something, right?
Yeah.
This is, I mean, it's okay, close, but like, what is it? Does it correspond to? Like, that was the reflection that we knew. Okay, so
Yeah.
what is this quantity?
So in this case, you're like really what you should think of is like the S and U oracles encode some Hamiltonian. The particular Hamiltonian is the guy written here, like this thing. This is a Hamiltonian, and you're trying to tell if like it has a big eigenvalue or not, right? And the way that you're expecting to tell is by receiving the top eigenvalue. And what I'm claiming is that this Hamiltonian you're measuring, it just has a rank 1, like it just has a random direction that it's like high on. Like a single, like this subset state for S is like the only direction where it's not 1/2. So it's kind of like, it's analogous to like having a flip around a hard random state, except it's just like encoded in a Hamiltonian instead of being unitary. Yeah. Okay. So the main thing I want to get out of this talk is this sampler thing, the proof of theorem 2. And before I get into it, I'll just say like this is like the critical point at which we like use the fact that there's, you know, you come up to me with a classical witness QCMA algorithm. And sort of before I explain anything, the moral idea is like, what would it mean if you had a classical witness? Well, the main thing it would mean is that you could reuse the witness. So like, if you were doing some task and you had a quantum witness, when you completed the task, maybe you destroyed the witness and you'd be really sad. But if I could make that witness classical, then I would just like repeat that. You know, I could like save a copy of it, or you know, maybe I have to create some quantum state that gets destroyed, but you know, I'll always have this classical witness to like keep using. So that's like what this proof will try to get at, and hopefully it'll be clear why I'll explain like where the quantum witness would like fall apart. So.
Break between 2 classes.
Oh, okay, sounds good. Yeah, so let's just like start with this simple setup. So, you know, remember we had this like distribution over yes instances. So there's like these sets on the floor and on the wall. And let me just imagine that like I ask your algorithm, like I remove the S set, so I remove all the points on the floor, and I ask your algorithm like, hey, is this spectrally correlated? The answer is definitely no when I remove all the points on the floor, because like, you know, that projector pi s is just 0. So the spectral norm will be 0. But you know, your algorithm, if it really solved the problem, it will say no when I remove all the points, and it will say yes when I have all the points in there. So what does that mean? The only way it can do that is if it must look at a point on the floor. It must be like looking at the points on the floor. So in fact, you know, this is basically the same idea as BBBB. If I measured a random query of your oracle, then I'll find a point that's on the floor. I'll find one of those points in S with like inverse polynomial probability. Okay? And this is, you know, so if I do this measuring thing, then I'll find one of the points. And here's like, if I had a quantum witness, when I measured that one point, I would like destroy my witness. I would just collapse it. You know, in our case, the witness is meant to be the subset state. So like when I measure the points, I just like completely collapse superposition and I can't use that state anymore. But you know, the nice thing about having a classical witness is that I didn't destroy anything. So why don't I just go again? So now I'll just ask the oracle like, hey, what about this guy? Where I put the single, you know, whatever point I found, I just put that on the floor. And I ask again. Well, you know, because I had a strong yes instance, if I only put a single point on the floor, that's also a no instance. So again, if I had all the points, my oracle would say yes. And if I have the single point, my oracle says no. So I must be looking at another point on the floor. So when I measure the query again, I'll get some other point, x2. And I just keep going. Until I put L over 100 points, I'll be able to keep spitting out more and more and more points of my Okay? So this is where theorem 2 comes from. Basically, like if I had a QCMA algorithm, it has to keep distinguishing any small set from the total thing. So that means it has to keep looking at new points. Like it can never stop finding new points. If at any point it stopped looking at a new point, it would get confused. It wouldn't be able to distinguish the big set from the small set. So, yeah. And the crucial point of this argument is that we're using the fact that the witness is classical to like, extract many points. If the witness was quantum, we'd basically be stuck at the first step. Like, yes, our verifier is going to look at points on the floor, but sort of it can only extract one of those points for you before it like goes poof. Like once that witness is gone, can't use it anymore. Okay. Okay, and the final step to get theorem 2 is like, well, there's this witness, but I could just guess the witness, and I get probability 2 to the minus q. So like if you're keeping track of what the theorem statement says, this is where the 2 to the minus q come from. So here I've written like a of w, but I could just like make it a of a random string, and yeah. Okay. So the rest of the talk, maybe this part I'll just gloss over, and I'll expect to talk about it more on Wednesday. Will be like, how do you actually prove theorem 1? So the thing I just showed you is like, if you, for the sake of contradiction, assumed that there was a QCMA algorithm, then I would have this, this box that solves this problem, like does the sampling thing. But the other flip side is that I should be able to prove now that the sampling thing is really hard. And if I can prove the sampling thing is really hard, then I would have a contradiction, and you couldn't have a QCMA algorithm. So, yeah, now we need to find some new techniques for proving lower bounds. Okay, so before I go too deep into like what actually happens, let me just like explain the vibe of like what's going to happen. So anytime you have a random object, a very natural like quantum thing to do is imagine that you actually got like an entangled object. So if I had like a random bit, I could think of it equivalently as like it's an EPR pair, but I just don't have the other half, right? You can also play this game with oracles. So like, if I got a random function, I can imagine it's actually like a superposition over functions, and I just can't see it all. Or like, I can't like, because it's an oracle, like I can't access it all. So this is like what we call the purification technique, or sometimes the compressed oracle technique. So basically that's what we're going to try to do here. We have this distribution over instances, what we call strong, and we're going to try to do this same idea. So instead of imagining we got a sample from this distribution, we're going to imagine we're actually interacting with some purified like quantum system. Okay? So this is what this slide explains, is basically like how you like do this thing. So anytime you have an algorithm that's querying a random oracle from some distribution, you could just write it down as if like all the oracles were just stored in superposition in some like register that you can't see. And every time you make a query to the oracle, you're really just like applying like this controlled projectors. Like you're applying some object that like looks at the description of the oracle and reads you out its phase, like its value in the phase. Okay. And okay, this is a because you guys are smart. Some intuition I've always had is like something about the entanglement between the purifying system and your adversary or your algorithm should determine if you're able to succeed. But somehow every time I go like write down an argument that's like bounding the entanglement entropy, it just never works, right? You'd like to say like you start out completely unentangled, like you don't know anything about the oracle register, and after a bunch of queries, you're like a little bit entangled to the oracle register. But it just turns out these arguments, like in this form, like seem to be really hard to make. So that's just like a side note. If someone could like actually prove some like generic statement, that'd be really cool. Okay. So this is just recalling what this strong distribution was. So if you remember, I'm sampling 2 to the n over 10, or L, many random points S1 through SL, and I'm taking U to be like basically the Fourier transform of ket S, right? So like taking the subset state and looking at its Fourier transform and taking the heavy points. So let's just like ignore the second point for now. So don't worry about the Fourier transform, that'll come in later. But like, let's just think about how you would purify the set S if there was no U oracle. So one way to purify a set a random, like, so one way to write down a random set is like as its indicator function. So like, everywhere you have like x is in x, you put a 1, and otherwise you put a 0. In this case, I'm allowing the elements like S1 through SL, they don't have to be distinct. So like, they could be the same. So instead of putting a 1 there, I'll put like an integer. Like it's how many times did like x appear in the set. So for those of you who do physics, this is called the Fock basis. It literally just keeps track, it's just like a multiset. So like every Lx just tells you the multiplicity of x in your multiset. Okay? And it just turns out, if I want to write the uniform superposition over multisets in the way that I described before, where I'm sampling L random elements and then building the multiset from them, this state here is like the uniform superposition. So this number, like these numbers, is like the square root of the probability of sampling a particular multiset. Okay. And it turns out, this is like where bosons come in, that like this, like multisets, okay, I don't know if physicists think of it like this, but bosons are just multisets. Like to me, it's just like, anytime you would have a multiset, you can like describe it using these bosonic operators. So let me just quickly run through like what they are, and I have about 5 minutes, so maybe I'll, explain what the boson operators are, and then like breeze through the rest of the slides, and I'll get back to it on Wednesday. So, what are bosons? So instead of writing down L1 through Lx, I like to imagine like there's a bunch of boxes with particles in them. So in this case, it would correspond to like the thing where it's like 3, 2, 3, 1, 2, 1, 0, 2. Like these would be like the numbers. And the bosonic operators correspond to like adding or subtracting elements from your multiset. So it's like I take one out. And the whole point of the boson thing is to account for the fact that like the elements in the multiset, they're not like unique, right? Like everything that has every copy of the 0 element is like the same. So like when you do the math, you have to account for like the number of ways you could remove a 0 if you wanted to remove a 0. So this operator AX is like what we call the annihilation operator. It's basically going to remove an element, remove one copy of X from your multiset. And it turns out that the number of ways to remove a copy of X is exactly Lx. There's Lx of them, so like I could remove any one of them. So I need to multiply this thing by a square root of that number to keep the normalization good. So this operator is defined so that it multiplies your state by the square root of the number of by a square root of Lx, and also decrements your Lx by 1. And similarly, I can define the dagger. This is literally like the dagger as a matrix. So if you wrote down AX as a matrix, you would see it's like a off-diagonal matrix. And if you wrote its dagger, you would see it's like a off-diagonal matrix, but like now above the diagonal. So what this guy does is he increments your X counter and also multiplies you by the new value of the counter. Okay. And this guy, he corresponds to like creating, like adding a thing X to your multiset. Okay. And another thing we should know is like if you remove and then add back in, it basically counts the number of operators in your the number of copies of X that you have. So for example, N0 in this case, it would like delete and then add back 1, but you can see that like it would just first multiply by square root of 3 and then multiply by square root of 3 again, and get you back to the same state. Okay. So I had this crazy equation from the previous slide, like this guy. Let's just quickly. Another thing I should tell you about is that there's like another way, like another basis for these bosons. So you can think of the thing that I described in the previous slide as like in the position basis, and I could just write down the Hadamard basis. So I'll just like this is just like a thing I can do, right? Like so. If I wanted to imagine the notion of like creating a boson in the Hadamard basis at position or at momentum, let's say, y, like all I'm going to do is I'm going to write it as the uniform superposition of creating them at position x with the corresponding phase. So like this operator here, AY dagger, is like creating, like adding a element in the Hadamard basis, adding y to your multiset in the Hadamard basis. And it's literally just going to correspond to the superposition of adding x to your multiset with a phase that corresponds to x dot y. Okay? So this is the momentum or Hadamard basis for bosons. And it turns out that if you look at that state that I had, the uniform superposition, and you write it in the Hadamard basis, you get this state. So it just becomes very simple. Like if you start from the all zero state and you added, added all the bosons in the zero momentum, or zero Hadamard basis, you would also get the uniform superposition over, like, if you looked at this in the position basis. Okay? So, I think I'm basically out of time, but you know, this is kind of like the first step in a kind of crazy process. But you know, once we know this is basically how you purify the S, like the process of sampling S. And it'll turn out that in this boson view, the Hadamard transform, like the U oracle, will basically look like some operator in the momentum basis, in the Hadamard basis. I'm not going to explain too much. Maybe I'll like gloss over it. But yeah, basically, like the point of doing all this is that it gives you a tool for analyzing what it looks like to measure, like to look at a point of view, right? Because it turns out that like the fact that we wrote down S in the Hadamard basis will mean that U kind of like naturally fits in. But yeah, it's going to be quite confusing, and I don't have enough time. But let me just conclude with like some of my takeaways from this, from doing this work over the past year. First of all, you know, quantum proofs, I mean, they're really something. They're really powerful, but it turns out, like, the irony, like, I feel like a funny thing about this proof, and the part that I did explain was, like, the sampler thing. It's kind of like, what we showed is, like, it would be way too good, like, it would be too powerful. Like, some of our classical proofs are too powerful, in some sense, like, because they allow you to solve these sampling things. Another way to think of this is like, you know, the power of quantum proofs really is like a use once power. Like, you know, like there are some problems that you can solve once with a quantum proof, but you should never be able to solve them many times. And that's sort of why you shouldn't be able to turn them into classical proofs, like QCMA problems. Second of all, like I said, like structure versus randomness, like I think it has a bigger, like it has like a really strange impact on quantum algorithms. Like, you know, like this, like, so one stumbling block that we had in the beginning was like, you know, I described this process where we sample like L elements from S, and we allowed them to be like the same. If you don't allow them to be the same, everything gets super annoying in a way that like makes the analysis like really hard. But it just turns out that like allowing them to be the same makes them independent. That's like the thing that we needed, right? It's like two elements of S can be sampled, like they don't exclude each other. And this like slight change gives us like so much more symmetry when we like go to write down the purification. Like it's the reason why I could have written like creation as 0 to the L. Because otherwise, like, you know, once I add one, the second one has to like consider where the first one is. So like really like small changes to like the structure of problems like has a big difference for quantum, for how you analyze it when it comes to quantum queries. And the third takeaway I think is that like there's so many more structured oracles. Like basically, you know, the thing that we ended up analyzing was like the minimum structure to get a problem that was in QMA. It's like, you know, sort of the Fourier transform is kind of like the most natural like thing you would try, but there's all these other problems that people care about, and all these problems maybe have a connection to other problems in cryptography and complexity theory, but I think that for a lot of these other problems, like Yamakar-Zandri and the expander mixing problem, there's been like a lot of work connecting them to like other things, whereas the oracle we consider is like a little more new. So to understand these other oracles, like we need, you know, a lot more tools and better ways to like prove bounds against like structured oracles. So yeah, maybe some open questions, but I think I'll just leave these here and then take questions.